Okay, yesterday we left off going over combustion, synthesis, and that was it. I gave you examples of combustion. We practiced it. I showed you the answer. I gave you 2 examples of synthesis. You guys did 2 practice ones, and then I gave you the answers of them. So what I want to do today is I want to talk about the decomposition, the single replacement, and the double replacement. This should go a lot faster because after I go over the example, you guys can look and you may already have it right. So when we take a look at decomposition, right, and make sure you guys have the paper out of the examples that I'm going over, because I know sometimes it's hard to read up here, and plus the screen doesn't even show it all. But let's look at decomposition. That's when you have one larger element that breaks down into 2 smaller elements. So decomposition is when you're going to end up having where it looks like I'll put it over here, A, B breaks down into A plus B. All right, so what we need to do is we need to break these 2 apart. Heat here just means that you have to add heat in order to break it apart. So for decomposition, it says hydroxides, which is your OH, that's a hydroxide, will often decompose with heat to yield water and an oxide. Magnesium can only form, and it's going to say Mg2 plus, and oxygen will form Mg minus. So when we break these apart by writing the charges, we're going to have Mg2 plus and OH minus. How can I find the charge of OH? Because I can't just look at the periodic table. What resource do you guys have to find the charge of polyatomic ions? Go ahead. The naming compounds packet. Okay? So in order to find the charge of OH minus, you guys would have to look at the naming compounds packet. So this is what's going to break down. But what you have to look at is the fact that the OH is also going to break apart. So when the OH breaks apart, that's how you end up getting the MgO and the H2O. This one is a little bit tricky because it doesn't look like, it's not like it's breaking down into 2 individual elements. But I believe the practice one that I gave you guys was also one that had an oxide in it, because I tried to make sure that it matched up with it. Number 5 is just like the example we're going over right now. So when you read the sentence below it that says hydroxides will often decompose to yield water and an oxide, you already know that one of the products is going to be water. So on your practice problem for number 5, make sure that one of the products is H2O. And then the other product is going to be an oxide. You know how when we talked about naming compounds, you take the normal name of the cation and then you change the anion to IDE. So any metal plus oxygen would give you metal oxide. For example, this is magnesium oxide. On number 5, it's going to be iron oxide. Okay? So that's how you get Mg2 and OH minus. The reason when you look over here that it's just Mg and O is because think of the charges. Mg has a +2 charge and oxygen has a -2 charge. So that's why you don't have any little subscripts below it, because it's already balanced. So I want you guys real quick to work on number 5. See if you think you got it right. I'll walk around. But for number 5, start with this sentence. You know you're going to have a water. And then the other thing you need to think about is how am I going to make that oxide? It's going to be a metal and O. You just have to make sure that the charges balance out. And then we'll go over it together. What are you looking at? This one or 5? It's each individual compound. For example, this says use Fe3. So you have Fe3 plus and Fe2 and O2 minus. So right now that does not balance. But if you change the little subscripts down here, you can probably get it to balance. Yeah, you get the subscripts if those numbers don't balance. For example, you have FE3 and O2. You can either do the crisscross method, or you can use the least common multiple. Brain's really going to be fried by the time we're done going over all this. And like I said, at the end of today's lesson, I'm going to give you guys the answers to all of these practice ones, and not just the answers, but it'll have like the one sentence thing below it that explains why that's the answer. So that should really help as well. Okay. So you guys can think about what you struggled with and what the actual answer is. What's that?
Can we get that now while we're going over it? So we understand
It makes
why.
sense from
I'll try that. I already checked to see who tried it and who didn't.
Is this a compulsion grade?
Yes. All it was effort. After Christmas break, when you guys come back, I'll have a quiz on Moodle. After we're done with objective number 6, there'll be a quiz on Moodle that has a couple of questions from objectives 4, 5, and 6, which were our more difficult ones. So that's when I'll actually assess you guys for accuracy. Right now, we're still just in the practice stage.
I'm really confused.
All right, do you guys want to take a minute to compare what's on there with what you got, or just go over each one? All right, let's take a look at number 5 real quick. The FeOH3. If you compared it to the one up above, you know that one of your products is H2O and the other product is going to be a metal oxide, meaning something with O. Now, you're supposed to use Fe3 right here because it's a transition metal, and I told you I'd never make you guess what the charge is. So that means you're going to have, and we'll just kind of write it up here, you're going to have Fe with a 3+ charge, and you're going to have O with a 2-. Because that O is going, it's blinking because it's recording right now. Yep. So the O is,
Can you start your own
yeah,
Khan Academy thing? Are you really?
no. I'm just trying to start something where people that don't understand it have more resources to use.
So is it recording your voice too?
Yeah.
So it's recording you right now?
Yes.
Hi.
All right. So the first thing I did is I wrote down the metal oxide and I wrote down the oxidations numbers. You were given Fe3, and you can look at the periodic table to see that oxygen is in group 6. Now this is where you can either do the crisscross method, like the guy talked about on the video from Moodle. You can do the crisscross method, or you can ask yourself, how many of each of these do I need to get the least common multiple, which will be 6, right? The only way to get these to balance out is 6. So that is when you're going to have Fe2 and O3. Because if you have 2 times positive 3 is 6, 3 times negative 2 is negative 6, they balance out. But it's the exact same as the crisscross method. Any questions on that one? Yeah.
Where did you get the H2O?
The H2O, you kind of have to know, and that's why I let you compare this to the example we did. Whenever you have a hydroxide, which this is a hydroxide, if you have OH, which is part of your decomposition, it's going to form a water. Kind of like combustion will always form carbon dioxide and water. So it's one of those rules that you have to know, but you don't have to memorize it. I just wanted to see if you guys can take number 5 and compare it to whatever question number it was, number 3 or number 4, on the examples we went over. So, yeah.
Would it matter if you put like H2O first?
No, it would not matter if you put H2O first. Not at all. Because they're both products. As long as you have both products there, it's Alright, let's take a look at the other one real quick, the other decomposition reaction. When we look at the other decomposition reaction, what does go back to the examples, because this is like one of the examples. What is the sentence that accompanies the example? Is there a little trick we need to know or anything like that? You're looking at number 5 on the first sheet. Yeah. What's that? Why is it going to have CO2 and metal oxide? What is CO3 right here? It says if it involves a carbonate. You know how the other one said if it has a hydroxide? This example says if it involves a carbonate CO3. So yes, this does involve a carbonate, so you have an example that you can compare it to. Hey, well this is exactly how this one is done, so this one is probably done similar. So if it has a carbonate, what's one of the products? CO2. And what's the other one? Alright, a metal oxide. So metal oxide means that we are going to have oxygen, because you have to have oxygen for oxide, and then the metal. The metal is going to be aluminum. It says use Al3, so that means we have 3+. What's our charge of oxygen? The charge of oxygen is 2 minus, right? So crisscross, or the same way I just talked about it in the other example, Al2O3. Is that what I have down on the practice problems? Right. Excellent. Any questions on decomposition? So with decomposition, the only ones I'll show you guys will be like these 4 examples you have. It'll either be one with a hydroxide or one with a carbonate. Or it'll be a very, very simple one where it doesn't have a polyatomic ion, where it just breaks down into the 2 smaller constituents, right? So, and if there's something like a carbonate or a hydroxide, I might even put in parentheses that little rule where hydroxide usually forms a water and a metal oxide. So you can at least take it from that point. What I'm trying to focus on is to see if you guys understand this concept of identifying the oxidation numbers and balancing each compound. Because if you guys can do that, then you're pretty good. Alright, so we're up to single replacement. We have, what, 3 more to look at? I want to go up to this example of single replacement. Alright, so I'm going to go over this single replacement one. Single replacement is any time that you have multiple compounds, but you also have something in its elemental form. Alright, so single replacement is when you do the little switcheroo of things. The first thing you need to do whenever you're doing a single replacement one is you need to break things down into its individual elements. So we have H, we have Cl, and we have zinc. Those are our 3 elements. Which 2 are going to switch? Which 2 elements are going to switch? Zn and H. So over here we have Zn and Cl and H. Now we're not done yet because we didn't look at oxidation numbers at all. So Zn, it says use Zn2. So that's Zn plus 2. Cl is minus 1. In hydrogen, remember Hoffer-Nickel? We talked about that. Because some people are, well, how do we get H2 over here when it was H by itself over here? Because normally you have millions and millions and millions of these compounds all throughout the solution. So you're going to have your hydrogens match up with something else. So that's why it's H2, because it's one of those diatomic molecules. It will always be H2. It will always be O2. It will always be F2, Br2, I2, N2, and Cl2. Hofburnickel. Those will always pair up to make 2. You're not going to see that element by itself. Now, Na, you see how that's not part of Hofburnickel? That's why it's Na alone. But if it was Ni for nickel, it'd be Ni2. So that's kind of how that works. All right. So now up here, we do the little cross and the little cross, and that's how we get ZnCl2. Or you can look at it like for every one Zn, we need 2 chlorines so that the charges balance out. And then we have H2. Any questions on that one? All right. Let's take a look at the other single replacement one then. Alright, so when we break this down, Tyler, what are our elements in this example right here? Sodium is 1, magnesium, and chloride. So all I'm doing is I'm breaking it apart so that I can see all the elements. Right? Which 2 are going to switch? Yeah, which 2 are going to switch? Okay, the Na and magnesium. Now the Na, what's the charge? +1, and chlorine is -1. Magnesium, it is not a diatomic molecule, so we don't need to have Mg2. And since we have 1 of each, it's already balanced, and that's, or you could crisscross. That's how you get NaCl plus Mg. In my mind, the single replacement ones are the easier ones. Those ones aren't too bad at all, right? So I want you to look at your practice problem. I'm going to walk around and see how you guys did on it. And then we'll finish up with our last couple of decompositions, or double displacement, and we'll walk through the move. Single replacement was the one you guys only had one to do. Calcium is in group 2A, so it has a +2 charge. So right now, and if you look at the answers I gave you for number 6, take a look at number 6 and see if you can find your mistake. Read the sentence below it. Okay. Very good. Now, and I'm not making you guys do this. Maybe in the future I will. I don't know. Because it's kind of hard for me when I walk around to look at people's papers. It's hard for me to see what you know and what you don't know if you're not writing down the charges up above it like that. Like some people, I can see, like right here, I can look at this paper and I can see that they wrote the charges down. So if they did not get one right, I at least know it's not because they don't understand the charges. Because really, there's only 2 parts to this. Do you understand how to find the charges, and do you understand how to either crisscross or balance it out? If you guys can do that, then you should be okay. And then there's simple things you need to understand too. What is a single replacement reaction? Do I know that that's where it does the Swippy swapping? Swippy swapping. Kind of like a flippy flop.
The next name of it is Flipper. Sounds like a Flippy flop. Wait, what was it called again? A Flippy flop?
So what do you, oh, you're doing CaCl2?
Yeah, Flippy flop. Slip and slide. Sounds right, right?
Yeah, let's see what you got there. Okay. All right. So most people look like they're all right with number 6. I will go over it with you guys real quick. All right. So let's take a look at question number 6, which was this one. All right, and for question number 6, I'm going to do the same thing that I did before. I'm going to write down all the elements, which is Ca, Ag, and Cl. I'm going to separate them a little bit just to give me some room. Now, which 2 are going to switch places? the Ca and the Ag, right? So over here we're going to have Ag, Ca has a +2 charge because it's in group 2 on the periodic table, and Cl has a -1 charge because it's in group 7. So we need 2 chlorines in order to make a balanced charge with the +2. Or you can use the crisscross method, right? And then you have Ag plus this. So that's your answer. The products are Ag plus CaCl2. Any questions on that one? All right, well, let's look at the last two then. The last two are double replacements. We'll go up here to my examples. All right, the first double replacement says use Zn2, so we already know that there's going to be a transition metal. But what I want to do is I want to break this down into its elements. HCl, I'm doing it on the wrong one. Hold on. There. All right, so with the double replacement ones, these ones are a little bit tricky, Jesse. If you take a look at it, you have to recognize that there are polyatomic ions. And you would have to look at your naming compounds paper to get the charges of those polyatomic ions, right? Or you don't really have to look at the paper because you know that Na has a -1 charge, or a +1 charge, so that means OH has to have a -1 charge. Otherwise, it wouldn't be written like that because it's written down like it's balanced, right? Same thing with H. If H has a +1 charge, that means your ClO4 is going to have a -1 charge. What two are going to switch places? Because a double replacement, they both switch. The Na and the H, the cations are what switch places. Now, I know what you're saying, and it's kind of the same thing, right? If you switch the anions, that's the same as switching the cations. But if you put this cation over here and this cation over here, that's how you get H plus OH minus, and they just rewrote that as H2O. Anytime you have HOH, just write it as H2O. And then the other one is going to be the NaClO4. So when you have a double replacement reaction, the first step is to break apart the cation and anion. The second step, switch the two cations. Third step, make sure that the charges are balanced out. If the charges are not balanced out, that's when you might end up having extra subscripts that you add down here, just in order to get the charges to balance out. All right, let's do one more together, and then I'll have you guys look at the two in your homework, and then we'll be done. All right, so for this double replacement reaction, first thing we're going to do is we're going to break them apart. We have Ba2 plus and Cl minus, because barium is in group 2, chlorine is in group 7. So when we break this apart, we have potassium, which is K, that's in group 1, so it's +1. PO4, what do you think the charge of PO4 is going to be? -3. You can either look, you're looking at the table, and that's fine. What's the other way that you can do it? You know how to do the crisscross method, right? So if this says K3 PO4, can't you kind of do a reverse crisscross like this when you're breaking it apart? You know that it's K3, so that means the 3 goes with the PO4, and this is PO4 1, so that goes with the K. So you can either look at the naming compounds or you can just crisscross. All right, Now what I'm going to do is I'm going to circle the two elements that are going to switch places, which are my two cations. So that means over here I'm going to have K plus 1 and Cl minus, and I'm also going to have Ba 2 plus, PO4 3 minus. I do my crisscross. That's how I get KCl. And I do a crisscross again over here, and that's how I get Ba3 PO4 2. Alright, so what I said was step 1 was break apart. Step 2, list charges. And this is exactly the way the guy on the video does it that I had you guys watch before we started. So you can go back and watch that, and maybe it'll make a little bit more sense. Step 1 was break it up. Step 2 is list the charges. Step 3 is switch cations. And then step 4 is crisscross. No idea how that's spelled, but crisscross. Maybe 2 S's?
Yeah.
I don't think I've ever had to write out crisscross in my life. So, crisscross. Alright. So, and the reason we're crisscrossing is so that we can balance the compound. Good? Does anybody have any questions on this? We went a little bit over on time. I think you guys got good notes. You have the answers for it, right? When we come back from Christmas break, we will review those a little bit more. But if nobody has any other questions, I'm going to start the Gattaca because we are down to like our 15-minute mark because I want to make sure we're able to get done. All right, good? And it's going to take me 1 second to save this.